All right, we're gonna go and get started with the seminar. Welcome everyone for the fall 2023 semester, and I'm glad to see everyone back for a packed house for the seminars this year. I know Dr. Aramova has done a lot of work curating speakers every week for 15 straight weeks. So hopefully you'll get a lot out of getting to see the presenters from all different focus areas, all different research areas, labs, industry, academics. Even if it's something that you aren't necessarily working on in your career or in your research focus area, there's a lot to learn. At the very least, you're going to see lots of things to do and what not to do in your own presentations as grad students as you start working in conferences. So even if you have minimal technical interest in what you're going to see, you can at least start getting some ideas on what your stuff is going to look like whenever you're on this side of the room. So there's no reason not to be here. So our first seminar for this semester series is going to be a collection of presentations by our own graduate students who perform internships and summer co-ops at different facilities around the country. We have Alina Jugan, Charles Ferran, Spencer Rippenbrack, and John Wen, who are going to talk about the work that they've done this past summer. To introduce each of these speakers, we have Dr. Maria Aranova, who is also the coordinator for our department seminar series.
Okay, now I know my name. Now we have 4 speakers, as Dr. Shan said, and we'll go in alphabetical order. So we'll start with Alina. And Alina is actually a senior undergraduate student, but she's doing already a graduate quality research. And she will share with us her experience at Oak Ridge National Lab.
Yeah, so hi, my name is Alina. I spent the last 10 weeks of my summer at Oak Ridge National Lab. I worked in the fusion energy division in the diagnostics and control group, where I primarily developed and completed the experiments for this project, as well as the relevant data analysis. My project is on the use of optical gas analysis to determine helium detection limits for the ITER DRGA prototype. Is anybody here not familiar with ITER? Yes, you are. Well, so the group that I was working with is partnered with the US ITER group, and I was working on their DRGA prototype. So what is the DRGA? The DRGA is the Diagnostic Residual Gas Analyzer. It is a multi-sensor system that is to be integrated into the ITER gas system. The prototype DRGA uses dual turbomolecular pumps to create vacuum chambers at high and low vacuum. And the reason we have 2 different chambers at different pressures is so that we can have a wider range of instruments that operate better at these different pressures. The purpose of the DRGA is to analyze the exhaust gas coming out of the fusion tokamak, and the composition of this mixture should be able to tell us whether the tokamak is performing as expected. Instruments include 2 different mass spectrometers, as well as 2 different plasma cells, which perform our optical gas analysis. So we're doing mass and plasma spectroscopy. So the plasma cells themselves consist of, they perform glow discharges, which is where you have 2 plates with a voltage put across the 2 plates. The gas in between the plates is ionized, gives off light. That light is what we perform spectroscopy on, and then we get a material analysis from that spectrum. The reason we have both mass and plasma spectroscopy is so that the DRGA can simultaneously resolve isotopic compositions of deuterium and helium with optical gas analysis, which is challenging with mass spectroscopy. And all the following tests use hydrogen as a proxy for deuterium. This is a very basic diagram of the DRGA, where we have our carrier gas, which would be the exhaust gas coming from ITER, going into first the analysis chamber, or AC. This analysis chamber has the first mass spectrometer, the QMS. Then we have the gas flowing through the first turbo pump into the interpump volume, named appropriately between the 2 pumps, also called the IPV. That has our second mass spectrometer, as well as both plasma cells. Then you have the second pump, and at the end is the 4 line, which is a system in ITER. It's a part of their vacuum gas handling system, which is connected to multiple systems in ITER. So the composition of the 4 line is relatively unknown at this point. And then it goes into the exhaust system. This is a cutout of the tokamak, and these are 2 of the DRGs in their respective port locations. This is not to scale. The DRGs are not this big. But as you can see, they're also connected to the 4 line or service vacuum. The motivation behind the work that I did this summer is called helium backstream. There are 2 main sources for helium in the system. First is helium from fusion in ITER, which is good. You know, the DRGA is intended to measure helium from deuterium-tritium reactions, and fusion enters the forward stream of gas in the DRGA. We have a little diagram up top, which will be on most of the rest of the slides. So the fusion helium comes in from the left and goes through the system. Then there's helium from backstreaming, which comes from the 4 line. This is bad. The 4 line has an unknown concentration of helium, and helium backstream from the 4 line complicates the detection of fusion helium. So we're trying to quantify how much helium is coming from backstreaming. So yes, that helium backstreaming leads to this research question: what are the detection limits of helium in a dominant hydrogen gas mixture? The first experiments that we performed were pressure profiling. The detection of helium is not only affected by backstreaming, but also by the vacuum conditions and gauge performance. So we were trying to determine what is the impact of the second turbo pump, the rotational speed as a percentage of full speed, on the pressure in the IPV, which is where our plasma cells are. The higher the rotational speed, the lower the pressure, the higher the compression, and thus less helium backstreaming. But lower pressures are not as effective for the plasma cells, which is why we have that red bar on the this axis here, which corresponds to preferred pressures for the plasma cells. We determined that in the conditions that we were operating at, the 40% speed is going to be our best conditions, under the system's restrictions, and following plots will have the 40% data speeds box. So the reason this is good is because it's at a good pressure for the plasma cells, and there shouldn't be as much helium backstreaming as would be with the lower pump speeds. After pressure profiling, we also looked at the effect of the turbopump speed on the intensity of the helium, looking at the 667 nanometer line. We have 2 sets of curves. Kind of the upper data points correspond to the optics plasma cell, which is just the brand name, and the lower data points correspond to the Henning plasma cell. Once again, the 40% data points are boxed here, and the helium intensity is lower than 40% as compared to the lower pumping speed, which is good, because the higher the intensity, the higher the helium presence, that means more backstreaming. Note that we also have quite a large gap between those 2 sets of curves. They have similar plasma cells, so you'd expect them to behave similarly, have similar gas intensities of helium, but unfortunately the optics uses a calibration scheme that we do not have access to. It is a quote unquote black box. So it is not a proportional reading from the current of the glow discharge into the intensities. This is some data for the helium and helium detection. This is the partial pressures. The optics, not only as a plasma cell, but because of the calibrations with the black box, it produces partial pressures of the gases that are present. So the lines correspond to the optics partial pressures, whereas the dots are for the mass spectrometer that is in the same location. The upper points and curve correspond to hydrogen, which match pretty well. That's good. But then you look down below and you see the line for the helium from the optics, but then you have this tiny little point all the way down here from the mass spectrometer, and this is not even at 40% pumping speed. All this data should be at the 40% pumping speed. This is at 45. The reason that is because a majority of the data from the mass spectrometer for helium was so close to this baseline measuring window that it was actually negative and thus not valid. So all of the 40% data was negative and not valid. the reason that we expect this to happen is, the ion trap mass spectrometer was a little bit of a distance away from the IPV. There was a pipe that had to go to it to get to the device. And then also in a dominant hydrogen gas mixture, the ability of helium to ionize and be detected by our devices decreases. This is the actual percentages of helium in our system by the partial pressures of helium and hydrogen with the optics and ion trap mass spectrometer. There's quite a large range of percentages for the optics, which is, not what we would like to see. All of these values, approximately 3.5% by the optics is significantly higher than we want and then we need to be able to accurately measure helium from fusion in ITER. Whereas from the ITMS, yes, that is less than approximately 0.5%, less than 0.5%. But remember, all of that data it's not trustworthy, it's not particularly valid. This discrepancy between the optics and the ITMS is not quite yet understood, but that's something that we're exploring. This is an actual this is the DRGA. This is the prototype of the DRGA. And once again, the gas comes in through the top, through the analysis chamber, through these two pumps in the IPV, and through the 4-line and to the exhaust. So to summarize, helium detection limits in the dominant hydrogen gas mixture were approximately 3.5%, which is not what we would like to see. There's also a difference between the optics and the Penning plasma cells, the intensities of the gas, as well as the optics and the mass spectrometers partial pressures. So a lot of this is not quite yet understood, but this project helps tremendously in determining how these different devices behave with respect to each other at different operating conditions, and then in pursuing our next steps. Some of the future work is calibration of optical gas analysis for partial pressure measurement. We want to take that Penning's plasma cell, not the optics. We want to take the Penning plasma cell, whose intensities we generally trust, and develop partial pressure calibration so that we can use that rather than the questionable partial pressures from the optics, just because we don't really know how it's being calculated. We also have in mind and have performed a configuration change to eliminate helium backstreaming. At the orifice of the second pump, we decreased the orifice size, which has initial results show that has decreased the percent detection of helium by approximately an order of magnitude, which is very, very good. So we're continuing on that work. And then additional prototyping work involves testing with deuterium, different gas mixtures, generally combining the plasma and mass spectroscopy measurements into composite measurements, and generally completing the prototyping work for the ITER DRGA. This is an acknowledgement as to where my funding came from this summer, and that is all I have for you today. Thank you. What questions do you have? Questions? In the back. Yes.
All right, so the only difference between optics and the Penning was the optics, you weren't sure what calculations were being performed by the sensor, whereas the Penning you knew.
Yeah, the Penning has proportional measurements. It's not, as in a non-technical term, as funky. The optics, we just do not know how the intensities are calibrated to create the partial pressure measurements. We just don't know, and we can't have that information, unfortunately. Davis?
So explain again why the ITMS was inaccurate because there was a pipe in the way?
Kind of. Again, that's another one of the things that we aren't quite sure about. But having the longer traveling path for the gas, with lower amounts of helium and a dominant hydrogen mixture, the hydrogen tends to, again, less technically, overpower the helium. So it makes its way through the system and the helium is potentially left out. That's one of the, I guess, hypotheses that we have for why that might be the case. And generally, the hydrogen might be just overpowering the ionization ability of the helium.
Thank you.
Any more questions? Yes,
So you have a turbo pump that you can vary the speed of?
yes, we have two variable turbomolecular pumps. We keep the first pump at 100%, and I don't remember the full pumping power, but we can vary it, yes, from 25% up to 100%.
Never seen it. What about, you have an option of, okay, instead of varying the speed of your turbo pump, you mentioned this with reduced orifice.
Yes.
Modification, couldn't you just put a throttle valve in front of it and get the same effect?
I feel like that has been discussed and would involve quite a lot of taking apart of things. Which is not something that I can accurately comment on.
The other one I wanted to ask is whenever you're comparing your mass spec results with the optical results, the magnitudes, 0.5% versus 3.5%.
Yeah.
Match up. What about trends? Do they both go up with the?
Yes, the trends are all similar. Well, it's kind of hard to see with this just because the helium was measured so close to baseline across all the data points. So by the mass spectrometer's understanding, there was almost negligible helium in the system, which is not what is actually the case. But all other trends are similar with the different intensities of the gases.
You had control over how much helium you're putting in the system, right? Couldn't you just put
Actually,
it where it was, where you could get results?
Well, we weren't introducing any helium into the analysis chamber. It was just pure hydrogen coming in through the top of the system. So that any helium we had present was known to be coming from the 4 line, which had a 1090 helium hydrogen mixture, which is generous to predicted 4 line concentrations of helium. So if we had helium present in the IPV, the stream of gas is going this way. If we had helium in here, we would know that it would be coming from the 4 line because there's no other place it would come from.
Last one.
So what if the flow through the system, you talked a bit about pressures, but how much gas are you putting in? Like, do you have a mass flow control or you're just opening it up?
Just a valve. We're just opening up a valve and matching, reading off the pressures in the system from the range gauges.
Well, you got a mass flow controller right there.
What?
You got a mass flow controller right there on the 4 line, that little black box.
Yeah, that's
Inside.
that's just for the 4 line. But the gas coming in through the rest of the system is yeah.
Just needle up.
Yeah, it's just needle valve. Okay.
Thank you very much. We'll have to move to the next. Okay, Charles is the next one. He graduated from NC State with Master of Science at NC State, and now he's continuing for PhD in reactor-dynamic and fuel modeling group, and he spent his summer in Granbury, Pennsylvania with Westinghouse.
Yes.
There's one question there.
So.
Was it?
We don't really have a specific, they've not given us a specific intensity, but we're hoping to have about 0.5%.
0.5%, perfect, there you go.
Yeah.
All right.
It is.
I'll start talking about my internship that I did up at Westinghouse in Cranberry, Pennsylvania. I was a part of the high energy fuel technology group under first, Aaron McGrew was the second one. Prior to that, there was a restructuring. But that didn't work.
I'm you're on Zoom.
There we go. So I'll give a little introduction and then go over the 2 projects and a conclusion. So not really needed to thank Dr. Avermo nice to introduce me, but I'm beginning year 3 of grad school, so in year 7 of school here at NC State. I work with another Dr. Avermo as part of the RDFMG group, and I'm working on modeling transients in CTF with a focus on the fuel and high burnup environments. The first project I worked on is pretty closely related to my research here at NC State. It was research with Cobra TF or CTF, which is a thermal hydraulics code that we use. The additional advantage of CTF over traditional, coolant thermal hydraulic subchannel codes, it's got a built-in fuel performance model that allows us to have a better idea of what's going on. In addition, it uses a 3 fluid model. So you've got modeling of a continuous liquid, a gas, and train droplets. You get a more accurate analysis of the coolant behavior. Moving on, like I'm doing reactivity insertion accents. So there's special entrants for modeling and simulation in all codes because of how quickly they happen on the order of milliseconds. Yeah, so this is a bit more detail on reactivity insertion accidents. So on the graph on the right, we see the reactor power and the fuel temperature. So we see just how quickly the reactivity and the power increases in reactivity insertion accident and the behavior that occurs in the fuel and clad. So because CTF has that built-in fuel performance model, we're not only looking at the coolant temperature, but also the cladding, fuel, and fuel centerline temperature. For this project, there was two, I guess, sub-tasks in that project. The first one was participating in the HERA benchmark, which is a benchmarking exercise proposed by Idaho National Lab for the modeling and simulation of reactivity insertion accidents in high burnup, but seeing as though it's an ongoing benchmark, this one was a zero burnup case. There were 14 cases given to be modeled, in my case in CTF, but there was a variety of other participants that modeled them in various fuel performance and thermal hydraulics codes. But the first focus was on the effect of the power pulse width on zirconium cladding with various hydride concentrations. More on the conditions, so the fuel was taken to be fresh uranium dioxide, pressurized water reactor pellets. The actual experimental data comes from the treat and the NSRR facilities, and it was a rodlet of about, I think, 16 to 18 centimeters. Now, on the right, we've got a diagram what the NSRR test facility looks like, standard research test reactor. One more thing about modeling in CTF. CTF is a thermal hydraulics code, which means it cares mostly about the coolant. And so we can't model the hydride thickness that's present in the cladding. So because of that, in my case, the number of cases that I could run went from 14 to 8. I was just ignoring the hydride thickness in the claddings. I also got the various power pulses. So to fully encompass the range of power pulses we see in this case, a rod ejection accident, we went from 300 to 7.5 milliseconds full width half max. And it's all normalized. So the results that I was looking at on the graphs on the left, we've got similar to what I showed earlier. In orange, the reactor power, so the full width half max of the power pulse. On the right, I included the cladding temperature and not the fuel temperature, since that's sort of the interface we're messing with. In all the situations, this is just 4 representative ones. In all the situations modeled, the cladding temperature was much higher than we would expect, maxing out at about 1400 degrees centigrade, where we would only expect it to go up about 1100. In all cases, I was digging through the source code of CTF as a secondary part of this project to figure out why those were so high. The gap conductance model hit the built-in maximum for CTF. So my guess was that initial, I submitted the results since that's what I had, but the error is not the right word. The discrepancy in the results between CTF and the experimental results were most likely the gap conductance model being insufficient or the fuel thermal conductivity not being able to keep up with the speed of the transient. Which brings me to the second part of that sub-project, improving the fuel models within CTF. So I've brought over a lot of that work from my internship to my research, and I'm currently working on implementing improvements to the CTF gap conductance. The main thing I'm looking at is for reactivity insertion accidents, the transient fission gas release is more important than for other kinds of accidents. CTF, because it's thermal hydraulics code, doesn't have a fission gas release model. So I'm implementing a transient fission gas release model to see if that makes a difference. The idea is it's going to cause the gas inventory in the gap between the rod and the cladding to increase, thereby increasing the gap pressure and causing a reopening of the gap during transient, which should lower the conduction between the fuel and the clad, lowering the clad temperature. That's the hope. And that's currently ongoing. So digging a little bit deeper into that, CTF's dynamic gap conductance model has the contact conductance, the fill gas conductance, and conductance due to radiation of heat. And so I'm messing with the contact conduction and figuring out when the gap is closed, when it reopens, if it reopens, and whether or not there's any instabilities with that open versus closed, since it's not a smooth curve. The second project that I did was a Westinghouse, they just gave it to me and said this would be interesting. It was very interesting. So it's modeling of rod ejections in ANCK Viper for a sensitivity analysis of their transient fission gas release methodology. The ANCK Viper is a Westinghouse built code that couples ANC8 and Viper to make calculations. So my task was to determine whether or not their current methodology was applicable and whether or not we could reduce, what the applicability was and whether any conservatisms could be reduced within that method. That would make it easier. And unfortunately, I can't provide any numbers since it's all proprietary, but the conclusion was, as we'd expect, transient fission gas release does cause an increase in pressure. So comparing the model behavior on the left, which has different, bounds than the limit on the right, this is from the NRC, so we can show the numbers. The current model has enough conservatisms to follow the NRC limits. However, we may be able to reduce the conservatism without reducing safety. Yeah, well, that's what I said. Another conclusion that we got was the power level at which the rod ejection happens doesn't have a lot of bearing on the transient fission gas release percentage. The trend depends a whole lot more strongly on the burn up at which the rod ejection analysis happens. So when compared to the limit, the simulated release is lower than the limit, which makes sense, which means we should be able to add a less conservative but still safe adder to the rod channel pressure. Yeah. So in conclusion, I had a really good opportunity to work on two projects this summer. One, which was very closely related to my research, which helped me progress, and another that allowed a bit of a deeper dive into field performance, which is something that I unfortunately don't know as much as I want to about. But got to do that, and I'm glad to be back at state to have working classes. I had a really good summer. Are there any questions, comments, concerns? Yes.
Yeah, I just had a question about like the hydride thickness concept, like in the model.
Yeah.
So my understanding is that in zirconium alloys, hydrides are not like, it's not like an oxide layer that's like a set thickness,
Yes.
right? So how are you, so I'm assuming, there's kind of hydrides that are like grain boundaries, all that stuff. And then there's also gonna be the oxide layer.
Yes.
So are you how are you modeling that? Because the hydrogen or hydride distribution in the cladding
It's not
is gonna be non-uniform, right? And then there's like all this mess, like porosity in the oxide. So are you accounting for anything?
Simple answer, no. CTF can't do that.
Okay,
So CTF can account for oxides,
yeah,
and
that's like a set thing.
yeah, it's you've got an oxide layer, this is the initial thickness, blah, blah, blah. CTF can't do the hydride layers, so I reached out to the benchmark organizers and they're like, this, pretend they're not there, like,
Okay,
it is what it is.
okay. That's good.
Yeah.
Thanks.
Any other questions?
I was just curious whether the gap conductance in the simulation, you said that it maxed out the thermal conductivity of the gap.
Yeah.
But the temperature of the cladding was higher than you expected.
Mhm.
So, if the thermal conductivity of the gas is higher than the model could handle, wouldn't that make the cladding even hotter than model set?
Yes, but the gap conductance is maxed out with the contact. Contact allows better heat transfer than gas, right? So my thought process is CTF, like at one point in time, because of various factors, the gap is going to reopen between the pellet and the cladding, which means that net conductivity is going to be lower. I think CTF is overestimating how long the gap stays closed, which means there's a higher net conductivity.
Okay.
And so it has to do with more of the timing of the timing of the gap reopening.
Okay. Understood. Thank you.
And I also personally don't like it, like, if there's an upper limit. I don't like upper limits. Not realistic. Are there any other questions?
I think we should move to the next speaker. With this full time virtual. Thank you very much. And our next speaker is Scott, who is also from the Academic Connection Group. And you'll talk about this time.
I do my internship at INL.
Yeah.
So hello everyone, my name is Kang, and it's my pleasure today to present my work during the summer. I work at INL. I work with Dr. Mark Hart in the reactor physics method analysis department. My project is to model the advanced test reactor using OpenMC, Qubit, and Griffin. So the weak highlights of my project is to create the first high fidelity adjustable mesh for the ATR and create a deterministic model for the ATR using the OpenMC and Griffin. So this is the highlight for my presentation. Firstly, I will briefly talk about the introductions and the computer codes I used, then turn into the result and the conclusion. Is there anyone that know the advanced test reactor? I know. So it is one of the kind research reactor in US. It has a very high flux reactor, providing variety of application, such as testing the material and using the isotope productions. And because we want to do many experience and upgrade the configuration of the ATR, so simulation and modeling is crucial for the ATR operation. And the ATR design analysis currently used in the INL, they use the MCMB code. And as you may know, when you want to upgrade or modify something in the model, you have to go through all the input in the MCMB input. So that's why we want to create some versatile and flexible model for the ATR. So in this work, we're using the conventional two-step method to develop a computational mesh, cross-section set, and 3D deterministic solution for the ATR. So in our work, we use OpenMC for analysis and the reference solution, and the Griffin for the neutron transport calculation. By using OpenMC, we can provide a powerful multiphysics analysis capability with substantial flexibility in upgrade new design and experiment for the ATR. And to connect the OpenMC cross-section and Griffin, we have to create a computational mesh. And in this work, we use a Qubit. So the overall process of verifying and validating the ATR model is depicted as follows. So to create the model, we use ATR specification. It is a classified document, so I cannot show the very detail with you. But using that one to create an OpenMC model and then generate the material-wise multi-group cross-section and convert them into the ISO XML format. In the same time, we create the computational mesh using Qubit. And after we achieve the cross-section and the mesh, we combine them into the Griffin code. So this is the computer code I use. So I want to briefly introduce them to you. OpenMC is well-known open source multicolor code for the neutron and photon transport simulation. It is suitable for advanced nuclear system utilizing high-performance computational system. It has the capability to handle complex geometry either from constructive solid geometry or from the computer-aided design. And it has the advance in storing and reading data in the format of the SDF5. And It also provides the Python API to make the input making more user-friendly. And in this work, it is used for its generated cross-section, and there are reference solutions. The second one is qubit. Initially, we want to use the Muse framework mesh generation, but it is pretty complicated for the ATR geometry. So we switch into qubit. Is it a geometry mesh generation software by Qualcomm and Sandiana National Lab? It has a capability to generate 2D and 3D meshes for finite element analysis and comparison of fluid dynamics calculation. It has the capability to provide automation control tools over the mesh height or the scheme of the mesh you want to generate it. And it also offers a Python API to make it the process more user-friendly. And the final one is for the transport calculation is Griffin. It is the combination of between INL and Aegon National Lab. It integrates the Gradient Snake and the Protest code suite. It was built on the Muse framework with quality assurance procedure. So within the Muse framework, you can integrate the Griffin with multi-physics calculation, such as using the Relap and Python. And so we can use currently at INL, Griffin is applied to diverse reactor design for Gen 4 reactor calculation. And I would like to present the result. And firstly is the OpenMC model. So as you can see, the 3D ATR benchmark model, it comprises of 43 distinct material. So it is very complex and have a diverse change of the material inside of the model. And for the multi-group cross-section, it is utilized for the cross-section and reference solutions, as I mentioned before. And in order to overcome the complexity when you want to modify the input, we create a modular approach to enhance the organization and flexibility in handling the model components. So we separate the for the fuel elements separate in the 1.5 and other materials and controls components, base structure components in separate 5. So if you want to just to redesign your base structure, you don't have to go through all of the input in one pit 5. As you can see in the flowchart to create the input for the OpenMC ATR is in the left-hand side viewer, and there are X and Y cross-section view of the ATRs generated in the OpenMC is shown in the next figure. And in terms of the normalized power distribution for the fuel elements, it agree pretty well with the benchmark using MCMB5. So the difference between them is within 10%. In terms of the loop is meaning. Can I show this? The loop is calculated as a summation of those fuel elements around this bar. So in that manner, the maximum difference is within 5%. In terms of the neutron multiplication factor, the OpenMC model agreed really well with with the benchmark result. As you can see, that only 10%, 10 PCM different in the 2D model and 100 to 150 PCM in the 3D model. For the mesh generation, the ATR geometry is variable in the XRY plane, but uniform in the Z. So the actual material changes, but not the geometry changes in the Z. A 2D mesh can be generated and then extruded into the actual direction. So the 2D of the ATR was comprised of 58 triangular meshes, element block, and one watt mesh element blocks. The blocks in qubit are used to group related elements to unify and see which each element with a block with the same material assignment. So after we generate the 2D meshes, we want to do the mesh side sensitivities. As you can see from the table, the finest cases is more than 1 million cells are 1 million cell in the mesh, and using 14 processor, it take around 1.5 hours to finish. And we try to reduce the mesh size. The 3 BCM differences in the K effective between the phi and cos meshes. If we use the 400, the mesh width of 400,000-ish number of cells, the differences is just 10 PCM and 3 times faster. And finally is the Griffin model. As I mentioned before, the geometry of the ATR allow us to do the 2D mesh it and then extend it into the z-axial direction. So in this manner, I created almost 13 axial blocks to accommodate the material changes. Then the from 2D mesh it's bent into 3D mesh is comprised of over the 700 blocks from the original 52 block 59 in the 2D blocks. As you can see in the figure is the discretization scheme for the axial direction. And finally, we already have the mesh and the cross section. So we do the material assignment link between the blocks and the qubit generation mesh. Then we use the diffusion solver in Griffin as a transport system solver for the Griffin. As you can see in the result, in terms of 2D geometry is agreed really well under 100%, 100 PCM. But unfortunately, in the last week of my internship, the HPC in INL went under reconstruction, so I cannot test another different transport solver. So we're using the diffusion, obviously make the 3D model performance worse. And for the conclusion, we create an OpenMC ATR model with the criticality test match with the benchmark. We generated a 5 2D ATR mesh for the cubic, the 2 linked OpenMC and Griffin. This mesh can be used for other applications like pure performance calculation. And the cost mesh is 2 times faster within 10 PCM difference in the K effective. And the model integrated between OpenMC, Qubit, and Griffin in terms of 2D calculation. It agrees real well with the reference from the OpenMC within 100 PCM. And for 3D geometry, the diffusion solver it's better the calculation, but mismatch with the OpenMC. So it emphasizes the need for a different transport model for more robust accuracy later. And that concludes my presentations. Any question and discussion are welcome.
Time for one.
Yes, please.
Thank you for the presentation. As far as I noticed, you did compare the results for the OpenMC and MCMP, one of your work. Did you also have a chance to compare the quantification time, the computation time, let's say?
Yeah, we do, but for the MCNP result, it is in the benchmark. So there are performance in terms of time calculation is not specified in the benchmark. So we cannot,
Just focus on the-
yeah. But I believe the Griffin, the Moose team is working on the huge parallelization for Griffin. So it can run up to 100 core per 100 processor per core for calculation.
Thank you very much. And then, next guy is Spencer. Spencer is the PhD student in reactor dynamic procurement. He joined us from Idaho, where he completed his BS degree, and he will share his experience of BWXT system.
Awesome. Thank you very much, Dr. Avramova. Once again, as was mentioned, I'm Spencer Erkenbrack, also part of the RDFMG group. It's a great group. Unfortunately, as part of my work this summer, all of the work we did was business proprietary. So you will see very few actual results, but I will try and talk qualitatively about what we did because it was absolutely awesome. This doesn't, oh, here we go. Okay, so before we get started, hold on, let me just check. This is going, okay, let's use these. So brief outline, talk about where I did my internship, what exactly we did, talk a little bit about the Banner project and its baseline specifications. Some of you, I'm sure, have heard of Banner. It's very awesome. And we'll move into talking about some burnable poison and control rod designs, talk about a partial core model that we developed, and also move on to some conclusions and some lessons learned. So I was at BWXT, specifically their Advanced Technologies Directorate, which in my humble opinion is the greatest of all of their directorates. It's located up in Lynchburg, Virginia. They have a bunch of offices up there, including like their headquarters. This picture here is all the interns that were in Lynchburg over the summer. There's like 50 of us. Some of us, well, most of us, oh, come on. Most of us were in this building, you can see in the background, but some people were at corporate, and some people were at the other facilities. These three pictures show just a couple of the projects they're working on up at BWC Advanced Technologies. Super awesome. So top right, we have rendering of the Banner system. So Banner is the BWC Advanced Nuclear Reactor. On the left, that reactor in the truck is the Pele reactor. I'm sure a lot of you have heard of that. It's for the Department of Defense. It's a very awesome project. It's rolling out pretty soon, hopefully. And on the very bottom, if you guys like space, BWXT Advanced Technologies does a lot of space nuclear work. This one is particularly exciting. It's a partnership with DARPA, Lockheed Martin, and NASA doing nuclear thermal propulsion work. Very awesome. They had their official press release right before we left our internship. So that was super awesome. So a lot of cool work done at BWXT Advanced Technologies. So what exactly did I do this summer? I was on the ARDP Banner project, specifically on the core design, which was really awesome. I've been wanting to try doing core design for a while, so it's great to actually have an opportunity to do it. Like I said, everything we did was business proprietary. I asked my people, I was like, what can I share? They said, anything you can find on the internet. So a lot of these pictures you, I'm sure, have seen and you will see again. The presentation they first gave us on our first day, I found it on the internet. I think they gave it here actually at one of our seminars like a year or two ago. So you guys will be seeing these again, but here, this is once again, artist rendering of the Banner system. It's supposed to be transportable via rail, truck, or plane. What we did as a project core design group, there were a couple of interns working on it with me. We did control rod and burnable poison design for the Banner core, among some other things, other miscellaneous tasks. We used MCNP, specifically 6.2, and we used BWXT's high performance computing cluster to do these analyses. So first off, let's talk about Banner, the BWXT Advanced Nuclear Reactor. It's a high temperature gas reactor. I like to call it the cheap version of Pele. It's a Craigslist version, because it's basically what it is. It's a great design, but the goal of Banner, if you read the documentation, it was to make a microreactor that was as cheap as possible. They don't have the Department of Defense pouring tons of money into it, so they want to make it affordable. It's 50 megawatts thermal, 5-year lifetime. You'll see a couple of asterisks. That means there's more to the story. I will share as much as I can. 5-year minimum lifetime for this core. It's longer, a lot longer. It's thermal spectrum, and once again, microreactor. They're using uranium nitride triso fuel and a graphite matrix. You'll see another asterisk there. Originally, they were planning on using uranium carbide, but using this new form, they can get a slightly higher fuel density. So that's why they went with that. Graphite cladding, apparently used to be in the works. I had to do a double take when I saw that. They are no longer planning on using graphite cladding, just FYI. It's gonna be 19.75% enriched, and they are, and this black bulk point graphite moderator, that is still planned. However, the team, mostly jokingly, I think, talked about wanting to just switch to a water moderated system. But yeah, it's a helium gas coolant, two configurations, so power generation or cogen. Power, literally just electricity. Cogen is electricity with process heat, which is very nice for potential customers. And yeah, standard 33% efficiency for about 17 megawatts electric. And the idea is if the customer needs more or less than that, or I guess can't really do less, if they want more, just stack up more units of banner. It's a set and forget system, so everything that's contained within like the reactor vessel, ideally they bring that in attached to the secondary side. Once it's done, after 5 years longer, they go in, pull that out, put a new one in, and keep going. So what exactly did we do? We did the burnable poison design. They actually had the core design team at BOC Advanced Technologies is awesome, a very cool group. They had specifically a bunch of neutronics guys and some thermal hydraulics guys. They had a bunch of very mature core designs they've already come up with for Banner. So what they did, basically, we showed up like, all right, here's some core designs we've got. Throw some control rods and burnable poisons in there and hit these design goals. They didn't actually say that, but it's kind of what it felt like. They did give us a few pointers, so they gave us some power peaking limits we had to hit, and they also gave us some K effective goals that they wanted us to hit as well. I have a picture of the Milky Way here because when we first started, felt like our design space was that big. We had basically the whole world was our oyster. We could do like whatever we wanted, which was kind of daunting at first, but ended up being a good experience in the end. They did give us a little bit of guidance as to, they said, hey, try using this particular geometry for both control rods and the burnable poisons initially, keep them the same, and then go from there. We did that initially, but ended up scrapping it for reasons you will see later. But yeah, for the burnable poisons, we determined the optimal layout to reduce radial peaking as much as possible. It's a long lifetime for a reactor core, so they wanted that to be burned as evenly as possible. So we experimented with a bunch of different things with the number of burnable poisons, the ton of different poison loading. So we tried different burnable poison materials, different burnable poison concentrations. We did a bunch of down blending, up blending, you name it. And obviously burnable poison physical geometries. We were successful in getting a pretty good flattening for the radial power across the core. It was great. So after that point, and after we had basically reached our K effective goals, we did a bunch of depletions. The depletions were a little tricky because they take time, and we were the whole summer, I feel like we're on a time crunch. But the depletions had two purposes. One was to see, the K effective versus the effective full power day plots. Once again, long lifetime. We want to see if we were actually going to make 5+ years, stay critical or above. And we also want to see the effect on our burnable poisons. Question number one being, do our burnable poisons actually burn, or are they just inserted permanent control rods? So this is a picture of just a generic burnable poison. Looks a lot like a WABA maybe, but generic. So yeah, one thing we learned, one of the biggest challenges we faced throughout the whole project was just a long lifetime. Kind of crazy, 5-year minimum, longer in reality. It was very interesting. So that was one of our biggest challenges. One big thing we learned is that our burnable poison and control rod geometry is that it's really important for our MCMP runtimes. So I say right here, overly complex designs take much longer. We had one design that was doing steady state K effective calculations in like 30 minutes, and had another design that was literally taking over 7 hours. So if the steady state was taking that long, you can imagine how long our depletions would have taken with that. We eventually scrapped that. We calculated it was going to take 21 days to finish. That was like a third of the internship, so we killed that one relatively quickly. Unfortunately, it was cool, but it was not efficient at all. So after we successfully, got our burnable poison design going, it's looking good. We worked on our control rod design. The control rod design, it was for a while, it was in parallel with our burnable poison design, but eventually we put it to the side and did it after our burnable poisons were designed. So once again, we just determined the optimal positioning of the control rods to meet our K effective goals, which were assigned to us by the people in our group for various shutdown scenarios. So yeah, similar to the burnable poisons, we experimented with different geometries, number of control rods and their positioning, etc. And again, geometry really does matter. Both the choice of geometry, so planes versus cylinders, as it's kind of shown by these cruciform blades versus these just annular rods. So the choice between one of those or the other actually really mattered. Oh, it mattered for us a lot for our run times. Just that type of decision, but also your geometry definition. So those of you who are familiar with MCMP, you define your cells with union, intersection, and complement operators, such as Boolean logic. You have to be careful because we did learn that if you overuse, and I think they do mention this in the manual somewhere, but if you overuse a complement operator, it will actually slow down your simulation significantly. So part of the project was going through and redefining a lot of the cell definitions to remove that complement operator. So, but in the end, luckily, we were able to create some great control rod and burnable poison designs for multiple cores that we were given. It was great. We generated a ton of data for the BWC core design team, which was very good. Super random side project we got. It was assigned to an employee in our group, but he got busy, pulled into, I think, Pele work. So we, one of our people said, hey, you're going to do this partial core model. So partial core models are great if they're possible. If you use the same number of particles, you get roughly the same computation times, but you can improve your statistics. But if you don't care about your statistics, you can reduce the number of particles you're running per generation, and it will increase your computation speed, which is great. Normally, you can just use reflective boundary conditions. This is a generic core. This is not related to anything. But yeah, those lines just represent reflective boundary conditions. So the main question was, when we were assigned this work, was, is it possible? Generally, it is, but in this case, no. So they had tried to do it in the past, doing a partial core model, but they'd ran into some super weird behavior and they were losing particles. So they said, hey, try it again, see if we still run that same behavior. So I did. Threw the entire core into a universe, made this pie-shaped wedge with reflective boundary conditions, filled it with the core. But we learned, and it was confirmed, that MCMP does not like doubly nested lattices with reflective boundary conditions. So we had an explicit particle model for all those triso particles in a lattice. A lot of triso particles. They explicitly modeled those in a lattice. We had that lattice within a fuel assembly lattice. And so when you pair that with these reflective boundary conditions, we would lose. So I ran 100,000 particle per generation run, didn't lose any, but when you did 1 million particles per generation, we lost 2. The breaking point is 10, but any lost particles is bad. So what happened is the particles would hit, for example, they would impinge on this boundary, and they would all of a sudden appear from here. And it was very strange. I think they submitted a ticket to the MCMP people, but anyways, we confirmed that yes, there is something weird going on. So that's an open ticket item for the MCMP people. So conclusions, lessons learned. Initially, we attempted to have the same geometry for control rods and our burnable poisons. It's a nice idea to make manufacturing simple, but not great, especially, I mean, maybe for other core designs, but for what specifically we were looking at, not great. We realized that designing to the core peaking goals first was actually the better way to approach it, rather than doing the control rods first and then throwing in burnable poisons. Something that we can all apply if any of you end up using MCMP, planes and complicated geometries, which I didn't talk about for a reason, some other complicated geometry they were doing. They greatly impact MCMP, so be wise when you're choosing those and just be aware. It can greatly increase your computation times and you can end up losing particles for no reason. Something that's very interesting, you probably were wondering this already, there's faster tools in MCMP to make design work like this easier. They knew that. So they had a kid over there looking at Parks. Parks is a nodal code. University of Michigan has a lot to do with that. So they were trying to get parts working so they can do this rapid design phase without having to wait. Even 30 minutes, even for a steady state, was too long for them. And then this last thing, I was told this by one of the employees, is avoid analysis paralysis. So we had that huge design space. We were sitting looking at this core thinking, we could put controls here, like we do this, but this might be better. So we were sitting there looking at it, and we learned, instead of seeing, you could sit and look at it and theorize all day about what you could do, where you could put stuff, but in the end, just get in there and put stuff in there, run it and see what happens and just get going. So it was a great experience. We were lucky that we were able to actually successfully satisfy all the goals they wanted us to with multiple of their core designs. I learned a lot about MCMP, still a lot to learn, but it was a great experience. BWC is awesome. And do you guys have any questions or comments?
We are running for a long time, but let's just,
Oh, right up here.
oh, yes.
And just a quick question, what was the geometry that took 7 hours?
That is unfortunately business proprietary, but it had, I'll just say it was not circular. Yes.
So when scoping out, do you have any engineering constraints in where you put the design? Can you build a control rod that would like crack immediately and still model it, or?
I mean, kind of, so we had to consider the control rod drive mechanisms. That was another reason they were interested in constraining us to, when we first started, they had an idea for a geometry, which may or may not have been like 6 or 7 hours. They liked that one for a couple reasons. One of them was for the control rod drive mechanism. So there were things like that we considered, and whenever we'd say something stupid, some of the more experienced engineers would say, that might not work or might not be feasible as far as manufacturing goes, control rod drive mechanisms. But yeah, so there were a lot of ideas bounced around, and many of them may have been shot down by the experienced engineers, but it was fun to be there in that atmosphere where we could think of something and suggest it and have somebody who actually knew what they were talking about say that might work or most likely won't work. So yeah, great question. Any other questions? Sorry, I think I went over a little bit, so.
I think we can put it on. And next Thursday we'll start on the. Thank you for all.
All right. I mean, it's.